Today's job is to calculate conservatism of a trait or bunch of traits. This is a collaboration with a PhD student. And I've done this, I've calculated conservatism before, quite recently. So I'm going to copy in across a few of these commands, adapting them. Now the only thing I'm concerned about, which may throw a spanner in the works and complicate things, is I'm trying to do this under a data set of incomplete data. So we'll be using a phylogeny of a whole bunch of things. Some of them have trait records and some do not. And it's a common limitation of various functions. On phylogenies, if you do these in R, you'll encounter that a lot of functions will require a complete data set or comparative data for each of your phylogenetic terminals, and I have no idea why people are always having this limitation, because comparative data is always incomplete. But such as it is, and if this may be the case here, and hopefully not. If it is, then that makes it difficult. But we'll see. I don't actually recall from using this particular function before. I'm using something called a delta statistic as a measure of conservatism because it works on categorical traits, which I often have. Also some numerical or continuous traits, which I just convert to categorical by things like quartiles and so on. So delta statistic, which is loaded through this command here in R. So let's just copy across. Read tree into R. And here that will copy down to where delta is calculated. Copy the phylogeny into our working directory. We'll close the old projects, so I'm not getting confused and deleting the wrong thing. So we'll need to read a phylogeny into R. In the old project, I was reading a bunch of different ones in, and a trait table. So we need to be checking the format of the trait table. Some kind of standardization of branch lengths in the phylogeny. Intersection between labels and a trait table. So let's say the trait table needs ordering for some reason, and then calculation of delta. Okay, so the first thing is to get the format of this. Let's have a look what this looks like here. Here's the trait table. Okay, very simple. 2 columns, species name and categorical trait. So I think we've got somewhere up here, we've got something in the same format. So this is one particular trait, female ITD. ITD is intertegular distance, which is a common way to measure the size of a bee. So distance between the start of the wings. Look at this and see if it is the correct format. Yep, that's good. Okay, so I think this is the file I need, so I'll just copy this in also. And here's the command to read trait table, trait data into our read table, give file name, header, which is a column names. Check if we've got a header. No, I don't have a header, so let's put header equals F. Row names. So in this case, this is specimen level trait data. So each of these corresponds to an individual specimen. An alternative would be species level, in which case you might have multiple records for each species, and that would have to be processed in a different way. Or phylogeny name nuke format, as always. Yeah. Read into an object called RT1 for historical reasons. It was reference tree 1 in the other project. No need to change the name. Okay, let's go into R. Loading a library Picante, which has a bunch of functions, including processes and functions for processing phylogeny. We'll leave that. And here's the specific code for this delta statistic for conservatism, which is put into this. I've given a path in this case. Okay, let's try and read the phylogeny. Good, no error message. And trait table. Good. Make a note of the data, which can be useful information as a project develops. Our phylogeny is 3,627 terminals. Right, so some kind of standardization required of the branch lengths, it seems. I don't recall I can't recall exactly what this is. Okay, tree edge length equal. Okay, so it seems to refer to zero length branches, of which there aren't any here. So maybe the function will crash if there's zero length, but it seems we don't have any anyway, so maybe we don't need this in this case. So making a list of with nothing in it except NAs at this point, but length is according to the number of terminals on the phylogeny. Okay, right into names. That is the name of each entry in the vector, sort of like having a column name for a one-dimensional variable. And put the tip names as those. Intersection between the trait table. Now these should be the same length. These should be exactly overlapping. Oh, which they're not. Okay. Oh no, they shouldn't be overlapping, of course. So the trait table is, so in this case, is only the input trait table only contains things which have been recorded, which is a subset, and the tree has a bunch of other things in it. So this will be a subset of. So this seems to be reordering the names. So some functions require this. And now we've filled out the trait table now with, you can see in this case we measured specimens. We didn't bother putting species names on there. That's a trivial thing which can be done through comparison with reference data. But we have reference data on the phylogeny, so these are included here. Reference data, none were, so thus don't have any records, and you can see the specimen data, which some of them also don't have and some of them do for this particular trait. Just one thing I just noticed is these are numbers. These are categorical traits, and one thing you have to be careful with R is, which you don't encounter with Perl, is that the variables and tables and arrays, they expect certain classes of data in there. In Perl, you can make a variable name and put essentially whatever you want. You put a word or a number, and R doesn't really care. And it will, when it perform a function, it will figure out what it is and do that accordingly. But in R, it expects a certain object. So the result is, if you have an R column, a variable which is expecting a number, and you put a character in there, then it will somehow convert this to a number, and you end up with something totally different. So this is one thing I'm a bit worried about here, and we need to be checking. But for now, let's just try see if this delta actually runs on this. Okay, looks like it's going to take a while. So maybe I'll call it there. So I'll put a link to this where you can obtain this our function for calculating conservatism on categorical data. This is the reason we're doing this is it seems to be a big niche in molecular ecology, which has persisted for a surprisingly long time, in that people are limiting the types of diversity that they retrieve from community DNA, particularly to overwhelmingly taxonomic in nature and better species level diversity, OTU, and so on. And we can better if we move towards functional diversity. This can be done. I'm curious. Curiously, not been done much, but the success of this will depend on conservatism. I think is one of the main variables. So this is why we're calculating conservatism here, and seems to warnings, but we do have an index returned for this. So next will be to calculate. So this is a delta of female RTD trait. Next will be to calculate this for different traits. Body size traits seem to be a lot more labile. I mean, you get certain taxa. Bumblebee is always pretty big, of course. Electids often quite small. But other traits are certainly a lot more conserved. Say certain life history traits, maybe parasitism in the bees. So we're going to be and sort of nesting certain nesting traits. So we'll calculate conservatism for a bunch of traits, and we think level of conservatism will determine the success of DNA-based trait assignment. Okay, so I think job done. Until next time.